I'm Sara Osman, a second-year PhD student at Leeds University. My project is supported by BGS and I'm looking at the vulnerability of roof collapse to Tephra loading using Ascension Island as a case study. The motivation for this work is that Tephra fall can increase roof loading and lead to collapse, and particularly for long span roofs or roofs in poor condition, collapse can occur at Tephra depths of just 10 or 20 centimetres. Over the past 500 years, there have been more than 2,400 fatalities as a result of roof collapse from Tephra loading, and that's summarised in this table extracted from the fatalities database of Brown et al. 2017. Despite the risks, there are still only limited data on roof damage following eruptions, because it's difficult to survey buildings before Tephra is blown or washed away, or clean-up and repairs are started. So this project aims to fill that gap by using a mix of laboratory tests, modelling and field surveys. I'm using the lab tests to identify the sliding properties of Tephra on different roof materials, and then I'm aiming to adapt the approach taken by building standards to design roofs for snow loads, so that roofs can be designed to withstand Tephra loading. I'll then use model simulations for a range of eruption scenarios on Ascension Island to investigate the vulnerability of the island's buildings to roof collapse. Ascension is a volcanically active UK overseas territory, and you can see here that it's in the middle of the South Atlantic. It has an area of 98 square kilometres and around 780 residents. There's evidence of both mafic and silicic eruptions, with the most recent eruption around 500 years ago. The thick fall deposits on the island include a mingle deposit, which suggests there may be little warning prior to an eruption. The isolation of Ascension means it will be difficult to evacuate people quickly, so it's essential that buildings can withstand Tephra loading. As the island is small, it's feasible to use it for this case study, and if our approach is successful, we hope it can be used more widely. I have some initial results from a probabilistic hazard assessment on Ascension using Tephra probe. I ran 1,000 simulations for each scenario, with wind randomly sampled from a 10-year dataset. This is based on a trachytic eruption from Spoon Crater, with plume heights of 12 kilometres on the left and 15 kilometres on the right, with a 50% probability of the plotted Tephra loadings. The map shows the main villages, the airport and the military bases, which are all towards the south and west. The contours correspond to mean collapse loads for the most common roof types on Ascension. That is long span roofs at 200 kg per square metre, tile and fibre cement roofs at 300, and metal sheet roofs at 400. You can see that as the prevailing winds are from the east, buildings in all the main settlements could be at risk. I'm now looking at a range of other eruption scenarios and will then use this as the basis for vulnerability assessment of the Ascension buildings. Models simulate Tephra loading on the ground, and roof collapse obviously depends on Tephra depths on a roof. The unfactored load depends on the Tephra bulk density, so the density of the whole deposit, which in turn depends on grain density and grain size distribution. Loading changes if the Tephra slides, and this is governed by the roof's material and its angle or pitch, as well as the internal friction angle of the deposit. Laboratory tests by Hampton et al. On metal roofs found that Tephra accumulated at roof pitches up to 30 degrees, but was mainly shed for pitches over 35 degrees. Although data for Tephra shedding are limited, structural engineers routinely assess snow loading on roofs, for example in the structural Eurocodes. These are a set of building design standards used throughout Europe and more widely, and I'm using these as the starting point for the Tephra analysis. In the UK, the structural Eurocode dealing with snow loading is BSEN 1991-13. It takes a characteristic value of snow load on the ground as the starting point, shown in this equation as SK, and that is then multiplied by two factors to obtain the snow load on the roof. The first is the roof shape coefficient, which I'll explain a bit more about, and the second is an exposure coefficient, which varies between 0.8 and 1.2 to account for snow being blown off in exposed locations and building up in sheltered ones. There are many options for the roof shape coefficient, but here are two simple scenarios. In the top diagram, for a simply pitched roof, the shape coefficient depends on the roof angle and is shown in the first line of the table. For pitches up to 30 degrees, the coefficient is 0.8, meaning the snow loading on a roof is expected to be 0.8 times that on the ground. For steeper pitches, a more complex equation is used, which basically leads to the coefficient reducing to 0 at 60 degrees, when all the snow is assumed to have slid off the roof. The lower diagram shows a multi-span roof where drifting can occur, and in this case the coefficient can reach 1.6 where there is maximum snow build-up. I'm aiming to use the lab tests to understand more about how Tephra slides on different materials, and then use these results to develop a similar approach for Tephra loading. However, before I can start the sliding tests, I needed to create synthetic Tephra, as it's not been possible to obtain large enough samples from Ascension. So I've been crushing and sieving commercially available mafic and silicic aggregates. To ensure the test Tephra is representative of real-world deposits, I compiled published data on bulk deposit densities for a range of eruption sizes and magma compositions. And as you can see from the centre plot, there's a wide range within single eruptions, between eruptions of similar compositions, and across different compositions, but no clear overall trend. So I'll be ensuring the deposit densities for the sliding tests fall within this range of values. I have also investigated the grain size distributions. I have some Ascension samples collected by Rich Brown from Durham University. The pictures on the left show these sieved samples, and the plot on the right shows the grain size distributions for the samples of pumice in pink, scoria in blue, and ash in green. This plot has grain size on the x-axis, with finer distributions plotting to the right. The black lines show the grain size distributions of my synthetic samples, and as you can see, these are very similar to the natural samples. These are the distributions that I'll be using for the sliding tests. This grain size plot shows the same test distributions, and the shaded area is the range of published grain size data for proximal samples up to 10 kilometres from source, and that's the maximum extent of deposition on Ascension before deposits land in the sea. The test distributions are at the finer end of the published range, but I'm focused on uniform loading on roofs, and I'm also constrained by the size of the lab equipment, and so I'm not considering clasts above 16 millimetres in diameter. I've also done shear box tests to obtain the internal angle of friction of the Tephra, which I found to be 36 degrees. This is much higher than the angle of friction of the load cell I'll be using, which is around 6 degrees, and so I can be sure that any sliding is controlled by the Tephra rather than by the cell. So the next steps are the sliding tests using the tilt table shown here. I'll be testing the mafic and silicic Tephra at thicknesses of 10, 20 and 30 centimetres by using some or all of the three-part cell. I'm testing sliding on metal and fibre cement sheets and tiles, and I can also test sliding at the base of the Tephra only by clamping the cell sections together, or within the Tephra by allowing the sections to slide over each other. And looking further ahead, I'll use the lab results and the eruption simulations to map the vulnerability of buildings on Ascension, and then I hope to be able to go to the island to ground truth the results. I'll also identify roof shape coefficients for an initial set of roof types and materials, which can be used when designing roofs to withstand Tephra loads. From all of this, I'll be creating a GIS roof vulnerability map that can be updated and improved as any new information on Tephra loading behaviour is determined in future, and will disseminate these results to the Ascension Island government via BGS. Thank you for listening.